Thank you for joining me today. We're going to talk about step 2 of factoring polynomials. This step is the factor patterns step. Now, I need to mention that if you're in Algebra 1, you're probably only going to be looking at the first three, and if you're in Algebra 2 or possibly in pre-calc, trigonometry, something like that, you might be expected to know the last two that we're going to look at. So I'm going to look at all these, but I'll focus on this first one. This is the most important, and that's the second thing I want to say. The difference of squares is really, really important. It's a hugely, hugely important factor pattern. If you get nothing else out of this recording, the difference of squares will save your life. The binomial squares, it's a great little pattern, and it's really important later on, like pre-calculus, calculus type stuff. That pattern can show up in funny ways and can be of value to know about. However, if our primary focus is on factoring regular polynomials, the next step, step 3, is going to go over how to factor binomial squares without recognizing the pattern. And I think, in my opinion, that doing it that way is actually easier than kind of squishing another pattern, another formula into your head. So I invite you to kind of recognize that this exists, and you're going to see it, and you'll be like, oh, there it is again. But you don't have to memorize this one, maybe unless you're in an advanced math class. Okay, and then finally, the difference in sum of cubes. Those ones are quirky little patterns that exist, and so it's really handy to have them kind of in your bag of tricks, although you won't see them nearly as often as the difference of squares. Okay, now this is where you pause the recording and write these down. Let me describe. I'll describe the first one for you. So the difference of squares is when you see a perfect square minus a second perfect square. Okay, now those perfect squares can be numbers, like 4 or 9 or 25, or they could be variables like x squared or x squared, y squared, z squared, or x squared, y to the 4th, z to the 6th power. All of those would be perfect squares. If you see that, then you know that you can break this down into two binomial factors. The first factor will be whatever the square root of the first term is, plus whatever the square root of the second term is, and then multiply that by a second binomial, that is whatever the square root of the first term is minus whatever the square root of the second term is. That's a difference of squares. Now, the binomial square is a little bit harder to identify. A squared plus 2ab plus b squared. That means that, again, we have a perfect square here and a perfect square here. It could, again, could be numbers, could be variables. But then in the middle, we have those perfect squares broken down to their square roots, multiplied together, and then doubled, so times 2. And so that's the kind of the hard thing to identify. We'll look at that. But what's interesting about this is that if you factor this, you get just that first square root of the first term plus the square root of the last term, and then squared. And remember, that means a plus b times a plus b. And we should have had several experiences at this point where we tried to do a plus b squared, and we said, oh, that's a squared plus b squared, and we got it wrong, because of course you have to do the foiling method. You have to multiply a times a and a times b. That's where you get that ab, and then b times a again. That's where you get the second ab, so 2ab, and then b times b, which is b squared. Okay, so that's an interesting pattern. Again, not quite as easy to spot in the trinomial form as some of these others. The second version of that is where instead of having a plus 2ab, we have a minus 2ab. And the only difference is instead of a plus b squared, we have a minus b squared. So it's really the same formula, just with the change in the sign there. Okay, And then the difference of cubes and the sum of cubes, I'm not going to go through and describe it, but I do want you to now pause the recording and just write these all down in your notes, whichever ones you feel like you will be needing. Okay, so let's go through and just identify some problems. And the first one, and again, this is the most important one, is the difference of squares. And it's easy to spot because you have a perfect square here, x squared, and another perfect square here, 25, and there's a minus sign in between them. So it's really easy. Now, what did I mean when I said that the perfect squares are easy to spot? Well, let me write a list here for you. You put this in your notes. 1, 4, 9, 16, 25, 36. Do you see what I'm writing down? These are the perfect squares. What's the next one? 49, 64, 81, 100. And you could go on and on and on, right? This is 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, and so on. And you could keep on going. You could go 11 squared, that's 121. 12 squared is 144. 13 squared is 169. 14 squared is 196. That's kind of funny. And then 225 is 15 squared. Those, if you have those in your notes, so you can kind of recognize, oh, that might be a perfect square, that will really help you out. You can use the square root button on your calculator if you want to identify perfect squares, but being able to visually recognize perfect squares will really help you out with this step. The other thing that helps out here is just recognizing you've got a binomial. Like, we don't really have any way of factoring binomials except greatest common factor and difference of squares and the sum and difference of cubes, if that's what's going on. Okay, so once we identify that this is our difference of squares, then we need to identify what's being squared there. And so we can see this is x squared minus 5 squared, and then we can write the factors. It's just x plus 5 times x minus 5. And that's it. Now, when you're first figuring this out, it's a good idea to just do the quick FOIL here and check. X times x is x squared. X times negative 5 is negative 5x. 5 times x is positive 5x. And 5 times negative 5 is negative 25. Negative 5x plus 5x is 0, and we're left with x squared minus 25. So recognize that's the check. That just shows that we did indeed find the factors that multiply together to give me x squared minus 25. But the answer is x plus 5 times x minus 5. Order doesn't matter. It could be x minus 5 times x plus 5. All right, let's do another one. And again, I've set this up so that it's really not much of a question of what's going on here. It's a difference. There's two terms. It's either a difference of squares or it's not. And at first glance, it's not, because 3y squared is not a perfect square, and 27 is not a perfect square. It's not on our list. But remember that the first step of all factoring problems is not looking for the pattern, it's actually looking for the GCF. And so do they have any common factors? And notice that 3 is a number factor for the first term, and 27 is definitely divisible by 3. It's really 3 times 9. So we can change this problem by first factoring out of 3, and then we're left with y squared minus 9. And y squared minus 9 is on our list. It's a perfect square, and so now we can factor this. This is y squared minus 3 squared, so we write y plus 3 times y minus 3. And then don't forget the 3 that we factored out at the beginning. That's also one of the terms, one of the factors, and so we have that separate. So 3 times y plus 3 times y minus 3. That's the complete factorization. It's actually 3 factors for this binomial. Let's do it once more. 7 minus 7m. So hopefully after that last one, you can see that the first step is to factor out a 7. We take out the 7, we're left with, well, what times 7 equals 7? And the answer is 1. Minus 7m squared, multiplied by 7, you must multiply the m squared by 7. Now, this one is tricky. And sometimes we have, first of all, we have trouble with that 1 there. It's really hard to think about. If you take out the 7, what's left? And remember that when we take out the 7, we're not subtracting at 7, we're dividing out of 7. So 7 by 7 is 1. So that's the first step. But then the second one is recognizing that 1 is a perfect square. It is 1 times 1. 1 squared is 1. It's the only perfect square that is the only number whose square root is itself. And then, of course, we have m squared. So we want to show you this, first of all, because I wanted us to recognize that the easiest one of all is sometimes the hardest one to identify, which is 1 is a perfect square. And second, to notice that this is kind of presented backwards of what we're used to. We're used to putting the variables first. But it's perfectly legitimate for the number, the constant term to be first, and the variable part to be the second. So this is still okay. It is 7 times 1 plus m times 1 minus m. And just a word on the order, notice that 1 plus m is the same as m plus 1, so it would have been fine to switch those around. But 1 minus m is not the same as m minus 1, and so that order has to remain. All right, there it is. That's the most important factor pattern. It's the difference of squares. If that's what you're here for, you got it. That's all you need. Let's turn our attention to a couple of more. And thinking about these as patterns and trying to identify the pattern. It's not as easy. The first step is the same as the difference of squares. We look at the first term, we look at the last term, we say, are those perfect squares? 4 is 2 squared, and x squared is x squared. So yes, they're both different squares. And so then if we took those 2, oh, and I did this wrong, I apologize. Let me change this because this isn't going to work. Did this in my head. It should have been a 4 there as well. Okay. My bad. Okay, so now let's look at the middle term. Well, is it the square root of the first term, square root of 4 is 2, times the square root of the last term, square root of x squared is x, times 2. All right, well, before, just a minute ago, it wasn't, and then we couldn't have factored this. It would not work, which is possible, but we're looking for problems that can work, so let's keep going with this. So it fits into our factor pattern of a squared plus 2ab plus b squared. So we know that it's a plus b squared. And that's what we're going to write here. So this is 2 plus x squared. Now let's check it. 2 plus x squared. 2 plus x squared. Remember, the big mistake everybody makes is saying, well, that's equal to 2 squared plus x squared, which is 4 plus x. That is not right. That's not the way it works. Instead, it is 2 plus x times 2 plus x. You FOIL. 2 times 2 is 4. 2 times x is 2x. X times 2 is 2x also, and x times x is x squared. The middle two terms can be combined. 2x plus 2x is 4x, so we have 4 plus 4x plus x squared, which is the original problem. Now, a lot of students at this point say, success, I did it. But notice, what do I have circled as my final answer? 4 plus 4x plus x squared. That was the question. That's not the answer. 4 plus 4x plus x squared was my check. I just checked it to see if my answer was correct, but my answer is 2 plus x squared. And that's the pattern I was looking for. Okay, let's look at one more. 3x squared plus 30x plus 75. Hopefully you can see that this is not a perfect square, that's not a perfect square, but they both have a 3 as a factor, as does the middle term. So let's take that out, and we're left with x squared plus 10x plus 25. And now we can see we have an x squared as the first term, and a 5 squared as the last term, and the middle term is 2 times 5 times x. So there's my pattern. And so this becomes 3 times x plus 5 squared. And there we have it. Okay, so there's the square of a sum, square of a difference. I didn't actually give you any examples of that, but it's the same thing. Okay, now let's do these last ones. I just wanted to show you that these indeed are true. These patterns are true. If we have a perfect cube, x cubed, plus another perfect cube, 27, which is 3 cubed, 3 times 3 times 3 is 27, then the formula says I can write that as x plus 3 times x squared plus 3x plus 9. Oops, I messed up. What did I forget? If it's x plus 3 squared, then the binomial is x plus, if it's x cubed plus 3 cubed, then the binomial factor is x plus 3. But the trinomial factor has a minus sign in the first term. Now, why is that? Let's check our answer here and see if this really works. It's a little bit more complicated. We're going to have to do 6 multiplications here. X times x squared is x cubed. X times negative 3x is negative 3x squared. X times 9 is positive 9x. And already we're kind of suspicious that this is not going to work out. We're going to have 6 terms, and how is that going to end up being 2 terms? 3 times x squared is positive 3x squared. 3 times negative 3x is negative 9x. And 3 times 9 is positive 27. And all of a sudden it comes clear. We have x cubed, negative 3x squared plus 3x squared is 0, 9x minus 9x is 0, plus 27, and that's what we started with. So our answer is x plus 3 times x squared minus 3x plus 3 squared, which is 9. Okay, that's the sum of cubes formula. We'll do one more, oh no, we've got 2 more here. Let's just do these really fast. Again, go back to that first beginning of the recording where you saw all the formulas if you need to remind yourself of what these are. I want to notice here, negative 5 and the cube plus 40. Of course, the first term is not a perfect cube because that negative 5. And 40 is not a perfect cube either, but if I factor out the negative 5, I'm left with n cubed minus, let's see, that's 8. 8 times 5 is 40. And 8 is 2 cubed. 2 times 2 times 2. So I have a difference of cubes. So the formula says, first of all, bring over that negative 5 factor, negative 5, times the binomial, which is going to be n minus 2, and then a trinomial, which is going to be n squared plus, it's the opposite sign, plus 2n plus 2 squared, which is 4. And there is my final answer. I'm not going to check this one. You can do that on your own. And then we'll go to the last problem here. Once again, there's a common factor, 17. If I take that out, I'm left with z cubed minus, 17 divided by 17 is 1. And so this is where we recognize that 1 is not only a perfect square, but it's also a perfect cube. So we have a difference of cubes again. So we can write 17 times z minus 1 times z squared plus 1 times z, which is z, plus 1 times 1, which is 1. So these are kind of surprising results, I think, and they don't show up very often. But it's interesting, and it's nice to have in your bag of tricks as you get deeper into algebra. Thank you very much for watching.